The title of this presentation is Integrability of a Hamiltonian Flow from the Poisson Bracket of Transfer Matrices for the Two-Dimensional Inhomogeneous Six-Vertex Model. To begin with the presentation overview, we'll be establishing some continuity from two previous presentations that I gave earlier in this series. And in those two previous presentations, I was interested in describing some more general characteristics of the six-vertex model, the fact that it can be defined as a two-dimensional model and also as a three-dimensional model. And in the two-dimensional case, the model can be thought of as square ice, and it had its residual free entropy computed over the torus in seminal work due to Lieb in the 70s. But besides this seminal work in which the value of the free energy was computed under a certain choice of the isotropic parameters, there can also be some other types of interesting objects and procedures and computations with the Poisson bracket like we have been mentioning in the previous presentation. And this is very much what we're going to be continuing to build on, the two-dimensional case of the inverse of the quantum inverse scattering type arguments or approaches, and further demonstrating parallels in cases or in aspects of interest of the subject for 3 dimensions. So we're going to be reintroducing a couple of materials and objects just to very briefly review, from which we'll further be discussing the two-dimensional case, as well as some other aspects of the three-dimensional case that we can tackle and approach with the information that we'll be mentioning. So this is to say that we'll be reintroducing very briefly the six-vertex model, the R matrix, and the Hamiltonian flow. And we'll draw upon similarities of computing the action angle variables for the nonlinear Schrodinger's Kamasa-Home partial differential equations, from which we'll discuss, again, aspects of the conjecture which we had described in terms of the Poisson bracket of the action angle variables, which is used to make some interpretation of the integrability of the Hamiltonian flow for the inhomogeneous six-vertex model that was first raised by Keating, Reshetkin, and Sridhar in the last sentence of their paper, in which they make this conjecture and say that would be of interest to explore it, as well as the fact that we're going to provide an overview of the computations with the action angle variables in the Poisson bracket and talk about how one can obtain the system of 16 relations from the 16 Poisson brackets from entries of the transfer matrix, and how this very much builds on our understanding of what to expect in the three-dimensional case for the quantum inverse scattering type argument and approaches. And in the last bullet point, as we say here, we'll demonstrate how notions of the quantum inverse scattering approach change with additional assumptions on the R matrix and the L operator. And these additional assumptions come from representation theory and certain algebraic constructions, because we're looking at the universal R matrix instead of the two-dimensional R matrix, and it won't exactly satisfy the Yang-Baxter equation, the universal R matrix. But nevertheless, these different types of characteristics and qualities can help us perform some type of computations, like we're going to talk about the computations that are used with the Poisson bracket in entries of the transfer matrix and ultimately characteristics of the two-dimensional monodromy matrix for 3 dimensions. So this is, again, the background for computing the action angle variables for the partial differential equations. And it's great just to very briefly rehash this again so that we can demonstrate how to obtain or how to look to obtain a type of system of relations from the Poisson bracket of the entries of the transfer matrix for the two-dimensional and homogeneous six-vertex model. And again, as we had mentioned, this is the statement of the Kamasa-Home PDE, in which we have the first time derivative of the solution given by the fact that from the remaining other terms in the solution, rather than this first time derivative u of t term, we have the highest order of the partial derivative of the solution as u of xxx, as well as other terms u of x, u of x, omega, which is some frequency term because the Kamasa-Home PDE can be used to model propagation of waves and other water type interfaces or propagation or wave interfaces, and finally a u of x xt term. So the Hamiltonian formulation for the Kamasa-Home PDE, as we have been demonstrating and exhibiting as a brief review from the previous time, was that we can define this m term, which is given by u minus the second derivative of the solution, from which we can define a system of Hamiltonians h1m and h2 of m. And from these two Hamiltonians, we can look to make use of some quantum inverse scattering type approach, which would lend itself to being to looking at and examining further characteristics of the L operators, the R matrices, Yang-Baxter equation, how the Yang-Baxter equation implies the equality of two partition functions for the model of interest, as well as from the fact that there can be a complicated system of Poisson brackets which can result to determining that an integrability or exact solvability condition holds from the Hamiltonian flow in the presence of inhomogeneities of the six-vertex model. And so similar methods by which one can introduce notions of solvability and action angle variables for the Kamasa-Home PDE relate to computations of the Poisson bracket for the inhomogeneous six-vertex model. And again, as we had mentioned, this paper due to Konstantin and Ivanov, in which from this seminal work, they demonstrate how some notion of Poisson structure can arise from the action angle variables, and that the Poisson bracket of the action angle variables are going to vanish. And this is demonstrating similarities in which how the Poisson bracket of the action angle variables in the seminal work that we have mentioned from the Springer reference in the last presentation in the series due to Fajib and Tashatan, how that relates to exhibiting that the Poisson bracket of the action angle variables vanish for the nonlinear Schrodinger's equations. And so the inhomogeneous six-vertex model reference, remember, like how we said, was this paper due to Kim, Reshetkin, and Sridhar, in which they drew upon information from the solutions to the Euler-Lagrange equation for establishing some conditions of integrability of limit shapes of the inhomogeneous six-vertex model. And again, recall how this reference from Reshetkin and Sridhar and Keating is related to another paper by Reshetkin and Sridhar, in which they talk about limit shapes of the stochastic six-vertex model. So it's very much looking at different types of conditions, whether you're imposing stochasticity, inhomogeneity, or maybe even colorability of the vertex model, and how what characteristics of integrability would result in the limit shape. And so again, like we had introduced, the six-vertex model has six possible configurations, and 2 arrows point in and 2 arrows point out, and there's also a height function representation, which is also given by the fact that the height function can be represented as a graph homomorphism. And then below the arrow representation of the six-vertex model, there's also a line representation of the same configurations of the six-vertex model. And as we had mentioned, the probability measure for the six-vertex model that's supported over the torus is given by W of omega normalized by the partition function of the torus. In this way, under the assumption that we're not enforcing isotropic parameters for the six-vertex model, is given by the fact that it can be written as A1 to the N1, A2 to the N2, B1 to the N3, B2 to the N4, C1 to the N5, and C1 to the N6. And so besides these basic definitions, the six-vertex model and inhomogeneities can be introduced from the following construction of the R matrix. And this is given by the fact that whenever we talk about the six-vertex model or other types of models of statistical mechanics, it can also always be important to determine what the disorder parameter for the model is, and certain regimes of the disorder parameter that can be taken, which in the case of the six-vertex model have connections with the fact that the six-vertex model has a conjectured phase diagram, which looks like this, where depending upon the regions and the threshold that you take relative to this disorder parameter, there can exist ferroelectric or anti-ferroelectric phases. And this can relate to either introducing disorder or other types of effects, such as in other models of statistical mechanics, like another classical model, like the Ising model, or the Potts models, or the dilute Potts model, and other types of general overview that I gave in the first presentation. And so from the Springer reference, we were making use of the seminal work due to Fajib and Tashatan, in which they demonstrated to us that for the nonlinear Schrodinger's equation, we can apply some Hamiltonian type of method, in which, like for the Kamasa-Home PDE, you can look for different ways to define a Hamiltonian or a system of Hamiltonians from the statement of a PDE. And then from the statement of the PDE, you can look to define some type of transfer matrix and quantum monodromy matrix in R matrix, and look at L operators, which can model in the difference or the influence of different boundary conditions in the configuration for the six-vertex model in a finite volume, to then study the infinite volume weak limit behavior. And so again, like we had mentioned, the Hamiltonian formulation for the nonlinear Schrodinger equation is from solutions to the system, in which you have the solution, which is given for like the nonlinear Schrodinger equation, which we had defined in the previous presentation in the series, in which the solution is the wave function psi, which you can take the complex conjugate of because it's a complex valued wave function. And then given by the fact that the Hamiltonian is also a function of the position of whatever position of the line we're at, as well as some strictly positive parameter C, which admits this representation, which is just integrating this expression against a standard Lebesgue measure over the line over the state space of the real numbers. And so to compute action angle variables of the nonlinear Schrödinger's equation, much like those for the Kamasa-Holm PD mentioned at the beginning of the presentation, we need the tensor product of the Poisson bracket. And the tensor product of the Poisson bracket is given by the fact that we can look at the tensor product between different entries of the transfer matrices, like what we've been mentioning several times is of interest to us, because that's the ultimate culmination of the computations with the Poisson bracket that are used in the quantum inverse scattering type method and the quantum inverse scattering type approaches in general. So it's just basically to say that if you want to make use of some information for the nonlinear Schrödinger's equation and a Hamiltonian method for the nonlinear Schrödinger's equation, you can look to define a transfer matrix, look at whether the discrete probability model that you're interested in, like the inhomogeneous six-vertex model, admits some type of representation with the transfer matrix, and also look to define the quantum monodromy matrix from the transfer matrix and from the L operators. And in this case, taking the Poisson bracket of the tensor product of these two entries of the transfer matrices just amounts to getting some other R factor term, as well as for the remaining argument in the Poisson bracket, taking the tensor product between these two components of the transfer matrix. In the Poisson bracket, as we had mentioned, just to briefly end our review in a couple of slides, is that it can take a few forms, given by the fact that if we have two functions, big F and big G, the Poisson bracket is just I times this integral of just subtracting two mixed order partial derivatives with respect to either the wave function or the Hermitian or the complex conjugate of the wave function of F and G. And on the other hand, from the second expression, we can see that the tensor product of the Poisson bracket between two quantities A and B, which are just two other test functions or test objects, which we're passing as parameters to the Poisson bracket, is given by the fact that it can be written as I times also an integral over minus L to L against the standard Lebesgue measure over the line, given by the fact that now this difference that we have in the previous line, we instead insert tensor products between each one of these terms appearing in each of the two terms in the difference. Okay, so when performing computations, we make heavy use of the following properties of the Poisson bracket, that it satisfies an anti-commutativity rule, bilinearity, Leibniz's, and Jacobi identity, which we had described in the previous presentation. And then the reference that we had mentioned near the end of the last presentation was the fact that we can look to adapt a higher dimensional quantum inverse scattering type argument with this paper exercises with the universal R matrix, because from the several authors, they provide and discuss the Dinkin automorphism, which gives rise to two of the L operators of interest that they have for the three-dimensional six-vertex model. And they comment that even though they don't write out all of the other family, all of the other L operators in the family that exists up to Dinkin automorphism, that there can be a way to maybe make use of this or to look into further the structure of the current L operators that they write. So this is just demonstrating that there's a richer algebraic structure when we increase the dimensionality of the six-vertex model by 1 to 3-dimensional. The fact that the L operator, it can be expressed in terms of mappings to unital associative algebra, like we had mentioned, as well as from the fact that from the other entries, which we had just vaguely defined and vaguely talked about in the last presentation, they can have connections with the construction of the universal R matrix, which relates to looking at tensor products of two spaces and defining differential operators over this tensor product of two spaces, which will determine the structure in addition to the algebraic structure of the other terms in the higher dimensional, three-dimensional L operator. Okay, and like we have mentioned from the Poisson bracket, one looks to carry out similar computations in which we have the universal R matrix, which can be given by a factorization of four components, three Q exponential factors, and the last term, which is for the K matrix, is given by an exponential of a tensor product. And then, as we had just alluded to, the Dinkin automorphism implies that rather than this one L operator, there exists, in fact, a family of L operators that can be determined up to the action of this Dinkin automorphism. And in 2 dimensions, an expression for the transfer matrix is obtained by holding one of the spectral parameters constant while varying the other spectral parameter, which is to say that in the reference that I made for Poisson structure and integrability of a Hamiltonian flow for the inhomogeneous six-vertex model, I directly adapted another expression of the L operator from Colomo and Franco in their paper, in which they provide an expression for the L operator under domain wall boundary conditions, which can then look to be expressed in terms of a product of L operators, in which lambda alpha represents the spectral parameters about 1 degree of freedom of the six vertex model, while the V of n minus I term represent the spectral parameters of the L operator about another remaining degree of freedom in 2 dimensions. So in 3 dimensions, we can play a very similar type of game in that we have to enforce an additional spectral parameter for the extra degree of freedom. And then this will hold several implications for the type of recursive set of relations that we can obtain from the L operator in 3 dimensions, and how at least this portion we can envision for 2 dimensions and 3 dimensions at the same time. And so from the L operators, I wanted to now provide some more information in contrast to a general overview in the previous information about the set of relations that are obtained from the transfer matrix of the inhomogeneous 6-vertex model, and furthermore, how this set of relations will help us study further the 3-dimensional 6-vertex model further in the next presentation in the series with information from the 2-dimensional 6-vertex model. And this is to say that there are a set of 16 relations, and they're given by several different entries in the Poisson bracket. So the thing is that one of the entries in the Poisson bracket that should appear in the front term, in the front position of all the 16 Poisson brackets, is given by just being a function of the parameter u, whereas all of the other terms which are given from the entries on the other side of the Poisson bracket, from the second argument in the Poisson bracket, are given as dependent upon u prime. So we just look to hold, for relations 1 through 4, we look to hold a of u fixed, while we vary the second argument of the Poisson bracket with a of u prime, b of u prime, c of u prime, and d of u prime. And then for the relations 5 through 8, after 1 through 4, we just hold b constant while varying all of the other terms in u prime, namely a of u prime, b of u prime, c of u prime, d of u prime, and so on and so forth for the remaining relations that appear in the set of 16 relations from the Poisson bracket that are parameterized in entries of the transform matrix, and which ultimately relate to the construction of the quantum monodromy matrix. And one of the parts of the argument for the quantum inverse scattering type of method and type approaches that we have to consider is that we have to introduce an alternative parameterization in whatever L operator we're interested in of the 16 relations from the previous slide, which are given in terms of entries of the inhomogeneous 6-vertex transform matrix. So this is given by the fact that we want to obtain to parallel the dimensionality of the dimensionality and the overall number of relations that's obtained for the Poisson bracket in the previous presentation from Fajiv and Tashatan, now given by the fact that we have to introduce additional prefactors in front of either the first and both the second terms, which are either, again, parameterized in either u or parameterized in u prime, and they precede these terms which we give in terms of script a of 1, script a of 2, script a of 3, or script a of 1 prime, script a of 2 prime, script a of 3 prime, as well as B, script B, script B1, script B2, script B3, script C1, script C2, script C3, and the same for D. So this is just to say that we obtain some different types of dependencies on different parameters, as well as sine of 2 eta terms, which ultimately result from they're ultimately coming from and resulting from the construction of the L operator and how the L operator can be used to study, rather than being able to study correlations or other types of properties of the 6-vertex model, it can be directly incorporated into a quantum inverse scattering type approach for demonstrating that some desirable properties and exactly solvable properties hold of the Hamiltonian flow of the 6-vertex model in the presence of inhomogeneities. And so explicitly, we compute several Poisson brackets from which terms in other Poisson brackets can be approximated by permuting arguments, i.e. by permuting entries of the transfer matrix in the Poisson bracket. And this is just given by some of the expressions which I directly copied from my paper. And I'm going to spend a little bit of time just talking about where these different presentations or these different formulas and expressions come from, because it's a pretty dense part of the paper, and I think it's on page 57. So it's just demonstrating how, if you look at one of the set of the entries of the 16 relations, like from the type which we have provided in the previous slide, these 16 relations for the 16 Poisson brackets degenerate to other types of expressions for different Poisson brackets, which are related to certain portions or entries of the transfer matrix. And we can see that we can express, many different types of symbols relating to the sign of 2 eta term, which appears throughout many different entries of the Poisson brackets, which we want to compute from entries of the transfer matrix, but also given by the fact that we have several products which occur of sigma minus or plus, or just sigma plus or sigma minus, which relate to the Pauli basis. And this is relating to the fact that the Pauli basis comes into play from quantum mechanics and making interpretations about the Schrodinger's equation and how the Heisenberg uncertainty principle holds true, because we can't observe a particle or an ensemble of particles with infinite precision simultaneously in the position and the momentum. But this is given by the fact that the Pauli matrices also appear as a basis in the exponential of in a matrix exponential, which is used to define a certain quantity, which appears in the quantum inverse scattering type method for the nonlinear Schrodinger's equation. So even though we're looking to apply a quantum inverse scattering type method and quantum inverse scattering type arguments in different types of situations, the Pauli matrices and other components which appear from quantum mechanics still appear in the construction, in the approach of this quantum inverse scattering type approach for inhomogeneities in the 6-vertex model. But rather than these first couple of terms, we can see that there are other family terms, such as given by product of sign terms and taking a summation over these signs with the product of the Pauli basis, as well as given by the fact that we can take one term by script P1, which is just relating to one of the entries in the Poisson bracket, which we can directly read off and obtain from the transfer matrix, which can be multiplied by this product of sign functions, which is relating ultimately again to the basis which is introduced in the L operator from the Colombo and Pronko paper, and how that can be used to obtain some type of information by either multiplying basis functions or terms which appear in the L operators, which can ultimately lead to a broader system and set of relations from the 16 Poisson brackets, which we obtain for the entries of the transfer matrix. And so we can think about further what are the types of entries from the 9 Poisson brackets that we obtain, and what would these entries be able to demonstrate for us and help us out in terms of the computations. And this is given by the fact that we can make use of, again, lifting directly some other parts which are given from the seminal work by Fadjiv and Tahirtan, from the fact that those authors, they demonstrate to us that we can approximate certain Poisson brackets, and in some cases, certain Poisson brackets, they can either be approximated, which can help us determine what is the approximate values of different entries of the Poisson bracket of various portions of the transfer matrix. And then that can be repackaged and interpreted in terms of an integrability condition and properties of the Hamiltonian. So this is to say that we can look to approximate the first Poisson bracket for the set of relations, the set of 16 relations for the inhomogeneous 6-vertex model, which is given by the fact that we can look to approximate this Poisson bracket, which shares in the feature that there's a sign of 2 eta term times n minus 3 in each one of the arguments of the Poisson bracket times a script 1 and an A1 and a script P2 and an A1 prime, which are given just by different entries which are parameterized in the L operators, which include expressions like we had demonstrated in this previous slide, namely basis of Pauli operator bases, as well as given by the fact that we have this sign function occurring and taking a product in a summation of the sign function. And we also have eta terms and other terms which are sigma z terms, which are other terms from the Pauli basis. And this can be used to approximate, for example, the first Poisson bracket. And the first Poisson bracket is good to keep in mind because it can demonstrate to us that there are some similarities and similar properties of the first entry of the Poisson bracket, which comes into the relation. And that can help us look at how this similarity propagates into additional complexities for other Poisson brackets and the other remaining Poisson brackets in the relation, and then how that can be used to determine what relations and what equalities are held for other terms in the Poisson bracket. So this is just given by the fact that we can approximate this first Poisson bracket by some sign of 2 eta term, which is a prefactor, squared, and then we multiply this prefactor by both of these terms which are subtracted, given by the fact that we can have an A3 of U term, a B3 of U prime term, dividing by the difference in U minus U prime. So this is very much just directly mimicking and directly applying the approximations for some terms of the Poisson bracket, which are introduced in the seminal work by Fadif and Takatan, and how one can use this type of property of the Poisson bracket, as well as other types of properties of the Poisson bracket, like we had mentioned, the Leibniz rule and all of those other three or four properties which we showed, which can allow us to obtain, in one case, an approximate type of expression for the first Poisson bracket, script P1. And for script P2, we can notice that there's a difference in the following. So we see that the expression on the previous slide for the first Poisson bracket appears in several other terms within the set of the 9 Poisson brackets that need to be computed for determining the first set of relations, the first set of the 16 relations. So this is given by the fact that if we want to evaluate the second Poisson bracket now, it gives a very similar expression given by the fact that we just have a different perfactor which is leading up to these two terms that we're going to subtract, an A of 3 of U and B of 3 of U, or A3U and B3U. And this is also given by the fact that this Poisson bracket takes this form, and we can see that it's just a little bit of a difference from the Poisson bracket which we obtained in the previous slide, because we permuted and we changed some sign of 2 eta term, which only appears in the first argument of the Poisson bracket and on the second argument of the Poisson bracket. So that ultimately amounts to one term instead of the square of this type of perfactor term appearing in front of the superposition of the terms that we're using to approximate the Poisson bracket. And the second expression with the entries of the Poisson bracket, which exhibit similarities, albeit more complicated expressions for the first Poisson bracket, is given by the fact that, again, for the third Poisson bracket, we have an expression which is given by sine of 2 eta only appearing in the first argument of the Poisson bracket, which can be approximately given as some complicated superposition. The fact is that the superposition at the end of it has a very similar term to what we saw in the first and the second Poisson brackets, given that we have a U over U prime, U minus U prime, and a U minus U prime term, which is normalizing both of these products. But it's also different from the fact is that rather than adding these two terms, we also have other terms which appear, which are adding their derivative of either B3 of U with respect to U prime or A3 of U with respect to U prime, as well as B3 of U with respect to U or A3 of U with respect to U, as well as different perfactors of the sign of 2 eta terms which appear. So this is demonstrating how the third Poisson bracket, it's becoming more highly non-trivial in comparison to the first and the second Poisson brackets in the relation. But the thing is that the third Poisson bracket still has some characteristics of the first and second Poisson bracket because of this last term. But then there are some other different cross terms emerging from different powers of the perfactors of the sine of 2 eta, as well as different terms which we're using to multiply the sum of the product of these partial derivatives with respect to U or U prime. And so the fifth Poisson bracket exhibits a little similarity, unfortunately, with the first couple of Poisson brackets, but it does still give some similarities not with the third Poisson bracket, but with the second in the first and the second Poisson brackets. So this is given by the fact that this is the fifth Poisson bracket, and there doesn't appear any power of sine of 2 eta anywhere in any of the two arguments on the Poisson bracket. And then this actually in turn results in a much more complicated expression, because in the first term of the superposition for approximating this Poisson bracket, we have some term which is again scaled in, that's scaled inversely proportional to U prime minus U and U minus U prime. But it's also given by the fact that now we're taking the sum of subtracting these two derivatives as well as multiplying by this constant C term, which is dependent upon I, but not allowing I to equal J, which appears earlier in the superposition for approximating this Poisson bracket. But then there's also another final term in the superposition, which again involves another type of subtracting two mixed derivatives. So it's demonstrating what are the type of more non-trivial characteristics of these Poisson brackets that emerge when we're computing them to higher order, and also when the fact that when there isn't any sign of 2 eta terms appearing. And a very similar set of relations for the Poisson bracket are obtained, which relate up to permutations of the entries of the inhomogeneous transfer matrix to computations of the Poisson bracket for 9 terms appearing in the first set of relations. So if we recall the previous relations that we got, we were able to get some relations by permuting these entries, like how we see in the first time B1 prime and A1, which are ultimately parameterized in the L operator that we had discussed, and that's expressed in terms of various Pauli bases. But the fact is that we can obtain a whole other set of family of relations by permuting these terms, in which we can see that if we look at these two terms which are given to each other, the first argument, which is given to the Poisson bracket, which has P1, script P1 and script of A1, it has script of B1 prime, but in the other relation, it has script of C1 prime. So it's demonstrating how we can permute some of these entries, say interchanging B with C, and we can obtain one relation of the Poisson bracket, which would then yield 9 other terms of the Poisson bracket, which we can compute up to permutation by either like permuting B or C or other entries which are parameterized in the L operator with each other. And we can see that the same type of relationship holds, in which for the second line in the first relation, we have script P1 and script of A1, and we can confirm that script of P1 and script of A1 also appear in the second entry of the Poisson bracket. But in this other Poisson bracket, we have script of B3 prime, but that's juxtaposed to the second entry of script of C3 prime, which appears in this Poisson bracket. So we can just see term by term for each one of the Poisson brackets, examining individually each one of the Poisson brackets. It's demonstrating how we can permute the entries from the transfer matrix and from the L operators, and how this ultimately allows us to get information about all of the sets of relation from the 16 entries of the 16 Poisson brackets from the entries of the transfer matrix, from only having carried out the computation for 9 Poisson brackets. And so, for the remaining relations of the Poisson bracket, one expects to obtain terms similar to those discussed in the previous slide, in which we had mentioned in the first Poisson bracket, we had the sign of 2 eta per factor squared, which also included a script of C1, which was multiplied by this difference of 2 terms. And then for the second Poisson bracket, we just had raising the sign of 2 eta term just to 1 power instead of squaring it with the second power, given by multiplying it by the same difference. And then we can see that with the third, fourth, and fifth Poisson brackets, those computations start becoming much more non-trivial, because we have different cross terms which result in slightly resemble in some ways the computations and the approximations which we have for the first and second Poisson brackets from the set of 16 relations from the Poisson brackets from the entries of the transfer matrix. But then we also pick up a whole bunch of other terms, whether it be the sum of this product term, as well as taking partial derivatives of products and taking the sum and multiplying it by superpositions of derivatives with respect to u prime or u. And so the tasks of interest that we want to investigate are relate to developing higher dimensional relations from L operators for the 3-dimensional 6-vertex model, from information on L operators for the 2-dimensional 6-vertex model. And this is given by the fact that we want to very much carry over notions from the 3-dimensionality of the L operator to the transfer and quantum monodromy matrices. And in doing this, we'll want to determine how notions of integrability change in 3 dimensions compared to the notions of integrability in 2 dimensions, which hold for the uncolored vertex model. And then we can further comment, all these ideas and putting all these notions together will allow us to further comment on how aspects of representation theory and the notion of up-to-Dinka and automorphism influence the structure of the L operator, and in fact, how we can obtain a family of L operators, which would then translate to some family of computations with the Poisson bracket and some family of computations and properties relating to the transfer and quantum monodromy matrices, and how we can very much generalize and look at, in different circumstances, notions of integrability and exact solvability. So again, like we had mentioned in the previous presentation from that reference that was given on exercises with the universal R matrix by Booz and several co-authors, like 4 or 5 co-authors, they introduced one 3-dimensional representation for the L operator. And as we had mentioned at the end of the last presentation in the series, is given by the fact that the zeta term is a mapping into a unital associative algebra. But rather than this term, we also had vaguely, kind of fuzzily or roughly defined some of the other terms which are appearing in the L operator. and how this L operator is one of the example of a family of L operators which can be obtained from the action of up to Dynkin automorphism, and how the Dynkin automorphism demonstrates how we can generalize and look at further consequences of integrability and exact solvability. But rather than the zeta terms, which are complex valued and which are mapping into unital associative algebras, we also have tensor products of differential operators, which is motivated from the construction of a tensor product of two spaces. And this is important because looking at the tensor product of two spaces comes into play from the construction of the R matrix. And the construction of the R matrix, when we're looking at a tensor product over two spaces and looking at constructing the R matrices in 3 dimensions from the Cartan matrix versus in 2 dimensions from the type of R matrices which we had introduced in the previous presentation in this series, which are parameterized in the magnetic fields H and V. These R matrices satisfy more algebraic properties, and the entries are related to the L operators, which in turn are expressed in terms of algebraic quantities, which very much lend themselves to certain properties and characteristics of either double Grothendieck polynomials or symmetric functions, which we can discuss in further presentations in the series. But this is just demonstrating how already we can very much gain a wider algebraic perspective just from probability and by looking at notions of integrable probability and how these notions carry over to the 3-dimensional 6-vertex model, i.e. the 20-vertex model in the triangular lattice, and how it gives us a very rich and more variegated and more broad interpretation. And so the concluding remarks that we want to end out with is that we provided further information on computations with the Poisson bracket for quantum inverse scattering type method in 2 dimensions, including a system of relations from the Poisson bracket that are parameterized in entries of the transfer matrix, as well as approximations to a few of the 9 Poisson brackets from the first relation, and furthermore, how we can bootstrap in a sense, or generalize, our computations from the Poisson bracket, from the 9 Poisson brackets in the first set of relations, and how that gives us the desired information up to permutation of entries that are parameterized in the L operator of all of the other entries of the Poisson bracket. And this is needless to say that obviously there are additional similarities between applying the quantum inverse scattering type method approach in 3 dimensions as in 2 dimensions. But as we've been mentioning, there can exist more complications to the dimensionality of the system. How many Poisson brackets one must compute in 3 dimensions versus in 2 dimensions, as well as the representation theory and how that relates to the properties that the universal R matrix satisfies, and how that very much relates to complex valued functions and mapping into unital associative algebras, which appear along the entries of the L operator, in addition to the tensor product of the differential operators relating from the tensor product of two spaces that we're using to construct the universal R matrix in the first place. And so for 3 dimensions, we can now carry over some notions more concretely where appropriate for studying 3-dimensional ice and vertex models. And this is also referred to as the 20-vertex model, in which the 6-vertex model exists over the triangular lattice, and it has different properties from the construction of the universal R matrix that we had just alluded to. And thanks for watching.